Good morning, everyone, and welcome to another morning of physics. Hopefully, you guys are all doing well this morning. Um, I'm sure that one of the things that's on your mind the most probably is, did I grade the tests? And unfortunately, the answer is no, I have not graded the tests yet. But I'll get to them this week. So probably I'll be grading them some tomorrow for the most part. So I should have them by Friday class. Anyway, so let's go ahead and jump in there and just talk about the new chapter. So because we don't have any homework due today, the class is going to be a little bit shorter today. We're just going to talk about the new stuff and then go over a sample problem, and that'll be pretty much it. Okay. The homework assignment is already up in Facts, Google Classroom, all that kind of stuff, so you guys can check the homework assignment. It's going to be problems 1 to 4 in 11A. So we are now in chapter 11, just section A, right? And so this new chapter is all about waves and it's about harmonic motion. Okay, so before we get started on this, let me just ask you guys any questions about anything before we get started? And how's everybody doing this morning? You guys doing well? Keeping yourselves busy? All that kind of stuff? All right. Things are getting, in my house, my kids are getting a little bit crazy, staying home and not going to school, not going anywhere. I mean, they go outside in our yard, and that's about it. But they're still getting kind of crazy, and I'm getting a little crazy myself. What about you guys? All right, so let's go ahead and get started on the new stuff. So, like I said, this is about waves, about harmonic motion, simple harmonic motion, and so let's just get into the idea of and talk about what in the world is harmonic motion. What is simple harmonic motion? Okay, and this chapter is going to start off talking about springs, right? And we're gonna talk about a pendulum, right? And we're gonna do some calculations on those things. We've already talked about springs and pendulums before, in when we've talked about, I believe it was when we talked about energy. But now we're gonna get into the actual motion itself, and let's just go ahead and jump right into it. Okay. So first of all, let's just look at a couple examples and think about how the motion works in those different examples. Okay, so let's think about a spring. Now we could think about a spring, let's say, that is suspended. So let's just do it this way. Or we could think about a spring that's on top of a table. Your book talks about a spring that's on top of a table. But let's just talk about a spring that is suspended. And we have some little mass, we'll just label M. It's hanging out here, okay? And so the problem is pretty much exactly the same whether it's suspended on some kind of thing hanging down or whether it's on a table. As long as we are just assuming that there's no friction, the process is going to be exactly the same. The only difference when it's hanging down is that gravity is also going to be in play, and what that's only going to do is it's going to pull it down a little bit more. And that's it. We can pretty much ignore gravity for the rest of this. The only thing that gravity is doing is just pulling it down a little bit more. And we'll address that when we get to the sample problem of what gravity exactly is doing. Okay, so let's suppose our start is right here. Before you pull it down or stretch it out or push it up, before you do anything, we're going to be stopped, right? And at this position, this is called the equilibrium position. And we've mentioned equilibrium before, right? And do you guys remember what equilibrium means in terms of physics for the most part? So what does generally equilibrium mean? It means something typically about the net force. What does the net force equal at the equilibrium position? This is a question. The net force, yes, is 0, right? So net force is 0 at the equilibrium position. And so equilibrium in general means your net force is 0. And so before you start, obviously your net force is 0, and it's not moving or anything else like that, okay? So let's go ahead and just get started into the motion. And so we're gonna do. You can either push. You can literally just push this up, or you can pull it down. Typically, it's gonna make a lot more sense to pull it down, but it'll work either way. So let's stretch it out. And this is not going to be drawn perfectly, guys, right? So I'm not going to necessarily have the same number of loops every single time. So let's stretch it out. When you stretch it out, and then let it go. And so when you stretch it out and let it go, so you're going to observe that as you stretch it out and let it go, it's going to go up and down, up and down, up and down. And if this is an ideal world and we don't have any friction and we don't have any kind of air resistance or any kind of like friction within the spring itself, it's going to continue to go forever and ever until you stop it or something like that. But this is a real world, and in real world we do have friction, so eventually it will stop. And the friction forces causing it to stop are called damping forces. But let's just think about our ideal world, okay? So once you stretch it out, and let's just let go of it from right here. So this is going to be a maximum position, right? And then after that, it's going to move. Let's say it's going to move up a little bit, like this. Let me see. Would it continue forever with gravity? Yeah, gravity's not going to make any difference. Okay, so as long as the gravity's not changing, which we're going to assume that we have constant gravity here, it would continue on forever. Okay, the only thing that gravity's doing is pulling it down, so it's making that equilibrium position lower than if there was no gravity. So if there's no gravity, this would be up a little bit higher, and that's it. Okay, so the gravity force is just adding on to the, or opposing the spring force, but it wouldn't have any other kind of effect other than that. All right, so let's call this our start position right here. So pull down to the max, or just arbitrarily. We could pull it down further, but we're not. All right, so that's going to be a start. Right at the maximum position, after we let go, we can notice some things, and let's just talk about three different things. Let's talk about the position. We'll call that x. We'll talk about the velocity, and let's talk about the force. Okay, so this right here is going to be our equilibrium position, and let me just draw this all the way over here, okay? So both of these things are below the equilibrium position, okay? So at this point, so we've pulled it down and we've let go. The x, we are going to say when we're below this point here, when we're down, this x is going to be negative, okay? So x is going to be negative here, all right? And let's skip velocity first and go right down to force. What do you think? What's the direction of force when you're at this position? Is it going to be up or down? We're going to say up is positive and down is negative. So when you're at this position right here, is the force going to cause it to go up, or is the force going to cause it to go down? What do you guys think? Right here. You guys with me? Will the force be pushing it up or be pushing it down at this position, below the equilibrium position? Up. Yes, you are right. Up, up, up. Yeah, the force is going to be up. So the force is going to be positive at this position. It's going to be pushing it up. And the velocity is also going to be positive, pushing it up at this point. So when you start here, we're going to say that at these starting positions, let's discuss this, the force is going to be both positive and max at the starting positions, because you can't have it go down any further. When you stretch it down, I mean, you could if you pulled it down, but once you let go, it can't go down below this starting point, okay? So the force is going to be positive at this point, and it's going to be maximum. It's going to be pushing it up, all right? And also at this starting point, that position is also, the x. We're going to do x. So x is going to be still negative here, and it's also going to be a negative max here, okay? What do you think right at the point in time when you let it go, what is the velocity right at that starting point? Any ideas? What should the velocity be at the very start? And we're going to get back to that position here in a little bit. 0, exactly right. So at the very, very start, when you just barely let go, it hasn't had time to build up any kind of momentum. That force hasn't really had time to act on it. So the velocity is going to be 0 here. But after you let go, the velocity is going to increase. It's going to be positive. The force is still going to be positive. And the position as you're below this equilibrium point is still going to be negative. Okay? Then let's just go to the point where you are, I should have had more of these loops here. Let's go to the point where you return to the equilibrium position. Okay? At the equilibrium position, once again, we are going to be, well, we're going to define that, at least for right now, we're going to define that as our 0 point for position. Okay? So equilibrium is going to be our 0 point for position. What do you think about, and once again, we're going to skip velocity. What do you think about the force at the equilibrium position? What do you guys think? Is it going to be positive, negative, or 0? At the equilibrium position, should the force be positive, negative, or 0? 0. All right. I'm seeing somebody say 0, and you are correct, right? So the force is going to be 0 at the equilibrium point when you're starting and every single time when you return to the equilibrium position. Why? Right? Because at that point, that force that your force due to gravity and your spring force are going to be completely equaled out every single time you return to it. Okay? But it's going to continue to move, right? You still have a velocity at that point, right? And that velocity is still going to be positive. Why? Because it's got some momentum, right? So the force was pushing up here, the force is pushing up here, and so at this point, although the force goes to 0, that velocity is going to have it continue to go up. The velocity is going to continue to go up just based on momentum, right? So it's not going to stop right away. It's going to take some time before that velocity is going to reach 0, right? And so we can go to the point at, let's look at a couple points here. And let's go to the point where it's gone up a little bit, and then we'll go to the point, and we'll call this, and I know these are terrible drawings here. We'll call this your maximum compression right here, up here, okay? And I think there should be a couple more of these little things here. Okay, so this is going to be your maximum compression. This is a little bit past your equilibrium position, and let's just think about those real briefly. So at this point in time, your x is going to be now positive. You've gone past the equilibrium position. You're up some, and so that's going to be positive. And your velocity is still going to be moving up because you haven't reached your maximum point, your maximum compression yet. So your velocity is still going to be I'm sorry, that should be velocity. Your velocity is still going to be positive at this point. What about the force? Is force going to be positive, negative, or 0 at this point? Negative, yes. Force is going to be negative. Once you go past that equilibrium position, what's the spring going to do? The spring is starting to scrunch up. It's starting to get compressed, and so it's going to resist that motion. It's going to want to go down. So you have a negative force over there while your position and your velocity are still positive, okay? And so that's going to be the case there. When you get to maximum compression, your x is still going to be positive, right? You're still above the equilibrium position. Your force is still going to be negative, and we're going to call that a maximum position right there, a maximum negative force. And what about your velocity at this point? When you get to the maximum compression, what should the velocity be? What do you guys think? So 0, yes. Velocity is now 0 at the top. So velocity is 0 at the top, velocity is 0 at the start, and you have maximum force. Maximum force here at the top, maximum force here at the bottom. Okay? And so keep that in mind when you have this process. Now this process is going to continue to go back and forth, and you can kind of make this sine curve going on, if you look at the motion, you look at the force, they're all going to be these sine or cosine curves. So as you change the position, so it's going to go back and forth. So this is going to get now the mass is going to go down, right? It's going to go down, 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 and then it's going to go back up, back and forth, and that will continue forever if you have no damping forces, if you have no friction forces. But in the real world, it's going to stop eventually. Okay. So when we look at this, we notice that the force and the displacement, right? The force and the displacement are always opposites. Okay? Pay attention to that. So down here, when we said our force is positive, the displacement is negative. When our force here positive, displacement is negative. When they're both zero, they're both zero, right? And then over here, the displacement is positive and the force is negative. Displacement is positive and force is negative. Okay? So the force and the displacement are always opposite in terms of their sign. And we're going to, the reason for that, we're going to call that force. We're going to call that a restoring force. Right? Why is it a restoring force? It's because the force wants to go back to the center, to the middle, to the equilibrium position. Right? And so that restoring force is always going to be opposite in sign to the displacement, to the position. Okay? And so we have a nice equation that we can use for this called Hooke's law. All right, and Hooke's law is basically going to tell us that F equals negative kx. Okay, and so what is everything here? F, of course, is the force. X is going to be the displacement or the position relative to the equilibrium. All right, so keep in mind, so at equilibrium, x is going to be 0, okay? And so x is just kind of relative to the equilibrium position. K, what is K? K is the spring constant, or the whatever. This spring constant can also work for, let's say, elastic materials. So it could be an elastic constant, okay? So but for right now, we'll call it a spring constant. That spring constant is always positive. It's always positive, okay? So this negative here goes towards that force. The spring constant is always going to be positive, so that your displacement and your force are always in opposite directions, right? The negative simply means that they're in opposite directions, okay? So it also means that force is a restoring force. It's pushing the opposite direction as the displacement, okay? So let's go ahead and just solve a problem, and then we'll be done, right? So we'll go ahead and look at the sample problem. You guys can open your books. I'm going to go ahead and open my book. See if I can open my book. All right, so it's on page, I think it's 521. Let me close this out. No, 591. Page 591 in your books. And let me just go ahead and go through the problem. It says, if a mass of 0.55 kilograms, so we're doing, so the mass is 0.55 kg. It's attached to a vertical spring, so exactly, so we can come back over here, exactly this kind of situation. So it's attached to a vertical spring, and it's going to stretch the spring 2 centimeters. So we have an x value, and it's going to be stretching it down. So our x is going to be, in this case, a negative, let me write it how they have it. So negative 2 centimeters. And we're typically going to use everything in meters. So that's going to be a negative 0.02 meters there for the position. Okay. What is its original, what is the spring constant? So we're solving for K. Okay, so let me read that again. If a mass of 0.55 kilograms attached to a vertical spring stretches the spring 2 centimeters from its original equilibrium position, what is the spring constant? Now what's happening is that it's being stretched to a new, different equilibrium position, okay? And so that x is going to be relative to without the mass on there, right? So we have this spring that's going to be stretched down, and the mass is 0.55 kg, right? And our x is downward, so x is going to be a negative 2 centimeters, or negative 0.02 meters. Okay? So how do you solve a problem like this? To solve a problem like this, you need to realize that gravity is in play here, and you don't just have the force of the spring. So we kind of ignored gravity up here in this previous situation, and now we're going to deal with it. So what is gravity actually doing? Gravity's pulling down, right? And in this case, the spring force is pushing up. But we have to realize that once you put this weight in and just have it there, that it's not moving, and so this is a new equilibrium. So you started at one equilibrium, and you're going down to a new equilibrium position. So what does that mean? If you're at a new equilibrium position, that means that your net force, once again, is 0. And if your net force is 0, that means that both of the forces that are acting on this mass are going to be equal. So let's go ahead and look at those two forces. So we have this mass of 0.55 kilograms. So we're going to just draw a very simple free body diagram. We have downward pulling is your force due to gravity, which we know is mg, all right? And you have your force due to the spring constant, so that's going to be your upward, we'll call that spring, all right? That's going to be negative kx, okay? And those two forces at this new equilibrium are going to be equal to each other. Why? Because the net force has to equal 0. Okay, so the upward force due to the spring and the downward force due to gravity must be equal. Okay, and because they're in opposite directions, they're going to cancel each other out to give a net force of 0. So I got a question here. Let me look. What is variable x again? So x is the displacement or the position. We're using them kind of interchangeably here, but it's the displacement. And let's see, is original equilibrium always the same as the spring constant? Is original equilibrium always the same as the spring constant? No. The spring constant is for the spring itself. So no matter where we start this position here, if we do this without gravity, if we do it on the Earth, if we do it on the moon, that spring constant is not going to change. It's relative. It's just got to do with the spring itself. Okay, and so we can calculate that. The only thing that gravity is going to be doing here is just going to be pulling it down more. And so the equilibrium can change. You can have different equilibrium points with the same spring. And that's just going to have to do with other forces that you have in mind. So the equilibrium position has got to do with where do you have the net force is 0, okay, which can change depending on how you set this up, right? Again, which planet you're on, whether this is straight down or let's say maybe horizontal or at an angle or something like that. So that's going to change. All right, so back over here. We said net force is 0 at this new equilibrium, and you have two different forces acting on it. So what did we just say? We said the two forces are equal. So the force due to gravity is equal but opposite direction as the spring force. And so we can say that negative kx equals mg. Or let's make that a little bit more appropriate. So kx equals negative mg. We're going to solve for k here. Remember, we're trying to get the spring constant. So we divide both sides by x. That's going to get us k equals negative mg over x. All right, so far so good. So let's just plug in some numbers, and then we'll be done. So k is going to be, well, m, go back to the problem. So this negative just comes from the equation. M is going to be 0.55 kg. G is going to be 9.81 meters per second squared. This is all going to be over x, and we said x is a negative 0.02 meters, or you could do this in centimeters, but we're going to try to keep everything in meters, kilograms, your normal SI units, right? And so that's it. The two negatives are going to cancel out, so we're going to get a positive number. You should always, always have a positive number for the spring constant for K. K is always going to be positive. So let me clear this out. That's going to be 0.55 times 9.81 divided by 0.02. Hit enter, and we're going to get a number, and that's going to be our number, okay? I think that we can just go ahead and round this off. So we can say K equals 269.77. You could say 269.8, or you could just simply say 270, okay? That's fine. If you say 269.8, that's fine too, okay? So 270 what? The units are going to be, so we have kilograms, meters per second squared per meter. Now, we could have these meters cancel out and just do kilograms per second squared, which would be fine, but typically it's not done that way. If we recall, a kilogram meter per second squared is a newton. So we're going to, at least it's commonly done, that the units are newtons per meter. But if you forget that and just go back and say, oh, hey, meters over meters cancel, and that's going to be kilograms per second squared, that's also fine. These two units are the same. It's just more commonly done this way. Why? Because this kind of makes sense of the idea of a spring constant. It's going to be a force per unit distance, all right? So it's how much force that spring is going to exert divided by that distance or per distance that you're going to stretch it out or something like that. So that's kind of the idea of why we leave it as newtons per meter. Okay, questions, guys? Any questions? Newtons per meter differs. No, it's always newtons per meter. You might find some examples where they make it newtons per centimeter or something like that, but I think for the most part you're going to see the spring constants are always going to be in newtons per meter. If you have, let's say, maybe a really weak spring, they might make it in newtons per centimeter or something like that. But for the most part, it's going to be newtons per meter. Is it different from Newton meters? Yes. Newtons per meter is much different from Newton meters. So it's different by a factor of meters squared, right? So if we have Newton meters, your meters are on top of the denominator. They're on the top here. They're not in the denominator. So here the meters are in the denominator. So Newton meters are equal to joules, which we've done before for energy. This is not an energy unit. It's just a spring constant unit. That's it. Anything else? This is literally it for today. If there are no more questions, we can end out. You guys can go on and just work on the problems. When it says from the equilibrium position, does it mean the displacement is negative? Yes, it means the displacement is negative if you're going down. And we know that we're going down in this case simply because it's a weight that's pulling it down. Okay? So from the equilibrium position doesn't necessarily mean negative, but if it's something hanging down, then it does. Okay? If that makes sense. All right? It's negative because it's going down. Down from the original equilibrium position. Okay. Any other questions? All right, guys. Have a wonderful day. I'm going to go ahead and sign out. And hopefully I'll have those tests graded before Friday. So I'm planning on Thursday is going to be my day where I'm going to do a bunch of grading. So hopefully you'll see your test grades by then. And then we can talk about them. I'm assuming everybody, I haven't even looked yet, but I'm assuming everybody has completed the test and all that. And hopefully well, I know there is a little bit of technical difficulties, but hopefully you guys work that all out. All right. So see you guys. Have a wonderful day. And, oh, one more question. Do we use FG in every problem? I don't know. I haven't looked at every problem. So if I just open this up. So use FG anytime we're talking about gravity. Okay. I would think that it probably would not be in every single problem, but I'm not sure. I haven't looked at them all recently. So if you open up the problems, here, let me see, practice. So sample number 1 is going to be using FG once again. Number 2, hang vertically once again, we're going to be using FG. Slingshot. So number 3, we're not going to be using FG. So right away, so when you see slingshot, you're going to be doing other things. You're not going to be using FG for that one. And also number 4, right? So you'll be using FG in number 1 and 2 because they're similar situations, but 3 and 4 are not. Do you always need to draw a free body diagram? Probably. I think that it's good to just draw what's going on. It's not that much work, right? So you just draw a little, diagram. Just make sure you understand what's going on. Like you don't necessarily need to if the problem doesn't say you have to, but it's a good practice. Just draw a free body diagram to kind of get an idea of what's going on. Draw pictures, right? Good. Okay. So have a wonderful day, everybody. See you guys. I'm going to go ahead and sign out now.